From your perspective or reference frame, the force of gravity is pulling me downwards. But from my reference frame, I feel weightless. No force is actually acting upon me, except of course the traditionally ignored air resistance, which I'll go ahead and ignore too. Unlike many other theories of Einstein, you can even prove this at home with a simple experiment. A water bottle pierced with holes spurts out water when stationary. However, while it's falling, no force acts on the bottle from its reference frame, making the water seem motionless within the bottle. Now, what does this apparently forceless environment remind you of? You're right, it's space. This equivalence between falling and floating in space is derived from Einstein's equivalence principle. What if gravity isn't a force at all? To understand this, we need to analyze the nature of straight lines. The shortest distance between 2 points is a line. On a curved surface, let's say the Earth, the shortest distance between the 2 points is the same line, which appears curved relative to a 3D observer but straight relative to a 2D observer. Such a line is referred to as a geodesic, and gravity causes motion of a body along a geodesic. Let's understand this better with another shape. Here's a 3D cone and a strip of paper which will help me identify its geodesics. Will this be a geodesic? Although it might seem so for a 3D observer, it's not, because there's an excess of paper protruding out, signifying an unnatural path, and we see here that it's curved. To get a geodesic, let's naturally wrap the strip around the cone. Therefore, the natural path of this ball is along this line. But wait a minute. If no force at all acts on a three-dimensional body like this ball, shouldn't it remain still in its initial position like that? There's one part of this explanation which is still missing. Time. In his special theory of relativity, Einstein proposed an idea of a four-dimensional world, 3 dimensions of space and 1 dimension of time. In simpler words, he's trying to say that to record an event, not only do we have to locate the 3 coordinates of space, but also the 4th coordinate, that's the time at which the event occurs. If we draw a space-time graph here, initially, the ball is stationary, but as soon as a mass is introduced, the ball appears to be in motion downwards in space, simply to maintain its geodesic path. It should also be noted that the ball moves diagonally downwards in space-time, which is downwards in space and forward in time. Therefore, we can say that the existence of mass curves space-time, which is the main principle of general relativity. The exact same thing is happening here. The moon orbits around the Earth due to the slope created by Earth's curvature of space-time. The velocity of the moon is insufficient to escape the slope, but sufficient enough to not collide with Earth. Similarly, if we zoom out, the higher mass of the sun causes an even higher distortion in space-time, enabling Earth's revolution. General relativity is more than just understanding gravity. It's about explaining the totality of existence. It led to the discovery of ripples in space-time, bottomless pits, global positioning systems, luminous active galactic nuclei, and who knows what more in the future.